Alright, the last thing we're going to look at for this set of notes is dealing with complex numbers. So, negative numbers do not have square roots in the real number system, and we've talked about that, right? We've been looking at problems where we had this situation, we've said not real, and that's because negative numbers don't have square roots in the real number system. But there is another number system in algebra, the complex number system, where negative numbers do have square roots. So for that, we have to introduce what's called the imaginary unit, I, and I is basically defined as the square root of -1, and I squared then is -1, because same idea we've been looking at, these would undo, so we would get -1 if we squared I. Okay? So to write the square root of a negative number in terms of I, we're going to use the property that if A is a positive number and we're taking the square root of -A, we can split that into the square root of -1 times the square root of A, which is then I times the square root of A. Alright, so let's look at problem number 1. I have the square root of a negative. So basically what we want to do is just rewrite it by splitting square root of -1 times the square root of the 25. And then by definition, the square root of -1 is I. And we know the square root of 25 is 5. So this is the way we usually write it, just the same as with variables we'd write 5x, right? For the next one, same idea. I'm going to split it into the square root of -1 times the square root of 3. Definition says square root of -1 is I. Square root of 3, there's nothing we can do to simplify that, right? So it's just going to be I root 3. For the third one, we have a -1 on the outside, so it's going to be -1 times. And then we're going to do the square root of -20, just like the two previous problems, and rewrite it as the square root of -1 times the square root of 20. So we know by definition the square root of -1 is I. We have to be careful here because 20, while not a perfect square, can be simplified, right? So if you need to, go over on the side and make your list of factors until you find the one that has a perfect square. So we're going to get -1 times I. We can say that's -I times the square root of 4 is 2, and the square root of 5 can't be simplified. So I'm going to write this as -2I root 5. Alright? When multiplying or dividing radicals with a negative, first we have to write each number in terms of that imaginary unit I, and then multiply or divide. This is one of those things that's always hard for me to remember. I want to just jump in with number 4 and say those are both square roots, so I can just multiply what's underneath. But because we're dealing with the imaginary system, we have to rewrite these first, okay? So this first one would be -1 times the square root of 10. This one is square root of -1 times square root of 5. And then we know square root of -1 is I. Square root of -1 is I. And then I have I times I. It works just like other variables. If we multiply like bases, we add the exponents. So I times I is I squared. And now we can combine what's under the roots. Another thing from the definitions that we have to remember is I squared is -1. So you're never going to leave an I squared in one of your problems. When you get an I squared, you're going to substitute -1. And this is going to be times root 50, right? Wow, this is a lot of work, and guess what? 50 can still be reduced if I make my factors right. So we can rewrite the square root of 50 as 25 times 2. So we know the root of 25 is 5. We can't simplify the root 2. So my final answer, -1 times 5 is -5 roots of 2. All right? For the next one, this one's a little bit easier than that one. Square root of 36, that's a positive number underneath, right? So that's just 6. And we know that the square root of -1 by definition is I. So this one is just 6I. That one's not too bad, right? For number 6, we're going to need to rewrite this one as well. And then, of course, this is going to be I over I times the square root of 120 over I times the square root of 6. Again, I works like any other variable. So if it is divided by itself, it cancels out, right? That's just 1. Now what we can do, we can rewrite square root of 120 over the square root of 6 as square root of 120 over 6. And then if we put that in the calculator, that gives me the square root of 20, right? Which, of course, we can break down into square root of 4 times 5, which will give me 2 root 5 for the answer. All right? Adding and subtracting complex numbers, these aren't bad, except for one thing that I need you to be on the lookout for. The biggest thing that I see with these problems that students will have trouble with, if you look at number 1, you see a binomial in a parenthesis and another binomial in a parenthesis. A lot of students will start to multiply these. So you got to be very careful. The operation that we're doing here is addition. This is not multiplication. The only reason they have parentheses in these problems is because these complex numbers are written as A plus BI. So they are indicating that 5 plus 7i is one term. Okay? So to add them, we can just bring that 5 plus 7i down. It's plus from the problem, and then just bring the 3 minus 4i down. and all we're going to do is collect terms, okay? We have numbers, and we have terms that have I. So I've got 5 and 3, that is 8. And 7i minus 4i leaves me with 3i. And that is in a plus bi form, so we're finished, okay? Of course, the only difference with a subtraction is we're going to need to distribute that -1 through that second parentheses. So I'm still just going to bring down the 8 minus 2i, but we're going to distribute that negative. So this is going to be minus 5 plus 7i. That negative outside the parentheses changes both signs. And now, just like the first problem, we collect like terms. 8 minus 5 is 3. Negative 2i plus 7i is 5i. All right? All right, now we're going to multiply them. And I see, when I look at this, a binomial times a binomial. So it doesn't matter whether it's polynomials, radicals, or complex numbers. If you're multiplying a binomial times a binomial, we got the same options. You can FOIL, you can distribute, you can use the box. I'm going to use the box. You do not have to. Any of the methods are fine. 3 times 4 gives me 12. 4 times negative I is negative 4i. We have 3 times I, and I times negative I is negative I squared. So I'm going to bring the terms that I got from the box. So just like when we do polynomials or radicals, those two terms in the middle are going to be like. So we can say negative 4i plus 3i just leaves me with negative 1i. And remember, from the last page, I told you we'll never leave an I squared in a problem. We have minus from the problem, and then I squared is negative 1. Okay? Be careful with the signs. So this is 12 minus I plus 1. So if I say 12 plus 1, that's 13 minus I, and that is in a plus bi form. Okay? So basically these are going to work the same way, right? They're just binomials times binomials. So 4 times 5 is 20. 4 times I is 4i. 3i times 5 is 15i. And 3i times I is 3i squared. Then if I bring my terms over, we're going to be able to add the middle two terms. 4i plus 15i is 19i. And we always replace I squared with negative 1. And then finally, 20 minus 3 is 17 plus 19i. And that is a plus bi. Okay? Then, of course, the only thing that's different about 3 is it's written as squared. So you can write it out twice. If you want to use the shortcut that we learned for this, you can certainly do that. This gives me 25 minus 10i minus 10i. Negative 2i times negative 2i is 4i squared. So we can add the two middle terms. Negative 10i and negative 10i is negative 20i. We'll replace the I squared with negative 1. And then 25 minus 4 is 21 minus 20i. Alright, one more of these. So we get 2 times 6 is 12, 6 times I is 6i, negative 5i times 2 is negative 10i, and negative 5i times I is negative 5i squared. So if I bring my terms over, if I have 6i minus 10i, that's negative 4i. I'm going to replace I squared with a negative 1. So this becomes plus 5. And then 12 plus 5 is 17 minus 4i. Alright. The last thing, finally, is dividing complex numbers. And we're going to end up with the same problem we had with radicals, that we're going to have an I in the denominator. And again, a math person decided I's in the denominator aren't good, just like roots in the denominator aren't good. So again, we're going to need to use a conjugate, okay? Because same thing's going to happen that happened with the roots. By using a conjugate, all of the I terms will go away. So a plus bi and a minus bi are conjugates. And this is just to illustrate, we've already seen this with the polynomials and with the radicals. By using a conjugate, we know that those middle two terms will be the same but opposite signs. So they're going to go away. And then because we replaced I squared with a negative 1, using the conjugate eliminates all of the i's, okay? So our last two problems, we're just going to multiply by the conjugate, and same with the radicals. The only thing I'm going to change is the sign between the two terms, okay? So on the top we get 4 times 2 minus I. I'm going to use the same trick here that I used with the radicals, right? I know if I multiply conjugates, I'm going to end up with a squared minus b squared, right? So a in this case is 2 and b is I. So a squared is 2 squared, which is 4. And b squared is I squared, which is negative 1, right? So in my denominator, I'm going to get 4. It's a squared minus b squared, so minus. And then b squared, look what I wrote down here. This is b squared, is negative 1. So we're going to minus a negative 1. And now that's going to become 4 plus 1 in the bottom, which is 5. The 4 and the 5 can't reduce, so that's my final answer. Okay? One more. The conjugate for this one is just going to be 5 plus I. So we get 8 times 5 plus I. And again, this time, A is 5, B is I. So A squared is 25, and B squared is going to be negative 1, just like the last problem, right? So we get 25 minus negative 1. So the top stays the same. The bottom is going to be 25 plus 1 is 26. And I think we can divide both of the 8 and the 26 by 2, right? So that gives me 4 times 5 plus I over 13. That should be the final answer.